Well, hello there. This is Craig Hain. My students call me Dr. Dell, and as you probably know, I have written a book called Teaching Math, and this is a video for people who are interested in teaching mathematics at the high school level. And this is a video on numbers, and in particular, it's a video about numbers and the way they should be taught for future mathematicians. Now, you may know from previous information or reading my book that we have a 10-tier program, and in the first 6 tiers we cover mathematics for students that are going to go on into science and engineering and technology. And then starting in tier 7 we have mathematics for students that think they might want to become professional mathematicians, and their requirements and needs, educationally speaking, are much greater than those that are just needed to go on into science and engineering. First, let me review for you the mathematics that they will know by the time they enter tier 7 if they've gone through the first 6 tiers. And then I will tell you what I believe is the appropriate approach to teaching them about the various number systems starting in tier 7. Well, the first thing is, of course, they have all learned about the real numbers, and in particular, we express them as points on a line, a straight line, and they've learned all about the rules of real numbers, addition and multiplication, and they've learned all about basically the operations, associative law, commutative, distributive, and so on and so forth. And they have done everything, all their calculations, pretty much with a calculator. And that's the first thing that we teach them. And in fact, we teach them this for the foundation, the first 2 tiers. So they actually learn this in tiers 1 and 2. Now, of course, the only numbers we actually deal with in ordinary everyday math are the rational numbers. We don't worry about so-called irrational numbers or transcendental numbers or anything else, because anything you can do with a calculator or a computer in practical math is, of course, a rational number. But they've had to learn about the decimal system and that sort of thing. Now, in tier 4, we actually introduce the complex numbers. And we do this in tier 4, which is the basically at the end of their pre-calculus mathematics. So they've already learned now about algebra and geometry and trigonometry. In fact, they'll have gone through it 3 times by the time they get through tier 4. We pass through it once, first time in tiers 1 and 2 at a very practical level. Then we do it using George Simmons' book in tier 3, and we do it again in tier 4 because we believe in teaching this in a tiered or layered manner. But complex numbers now, as you very well know, and there's a whole video on that, are simply numbers now in the plane. Instead of a real line, you now have the plane, and you have 2 axes. We call one of them the real, one of them the imaginary, and then complex numbers are any points in this plane. And I have a whole video on this that you should watch if you're not clear on just what we do in tier 4. Then in tier 5, we begin to use Mathematica extensively and Wolfram Alpha, and we introduce what are essentially the hyperreals, because we are going to use, in particular, we're going to use infinitesimals. Now, I also discussed that in the videos, the earlier videos where we're talking about the first 6 tiers. And of course, all of this is done in a heuristic manner. We are not attempting to be rigorous at all. We're not trying to prove theorems. We do give valid arguments when it's appropriate, but we're not in any sense of the word trying to treat this the way a professional mathematician would. We treat these number systems heuristically, even though it's all correct and it would all be consistent with the theoretical approach, but in a way then that makes them very useful. As you will have learned, if you don't know already, if you go through tiers 5 and 6, infinitesimals are a marvelous way to prove theorems in calculus that otherwise are too complicated and difficult at this level. We don't believe that you should get into extensive or rigorous treatments of things until you get into tier 7. Scientists and engineers need to know how to do valid arguments but they don't need in-depth theory. At least that's our position on this. Now, what happens when we go to Tier 7? Tier 7 is where we're now going to begin to teach the mathematics that a future mathematician might need to know. And this enters now into a whole new arena. So let's talk about the number systems and the way we would present them in Tier 7. Well, the very first thing we would do is we go back to the very beginning and we introduce the natural numbers, which are just sometimes called the counting numbers, 1, 2, 3, and so on. And this is denoted by the symbol n, the natural numbers. Now, at this point, we begin to give a rigorous presentation, and so we use what is a standard mathematical approach, which is the axiomatic system, and we start with a set of axioms, which define, in essence, the undefined terms, and the axioms define the natural number system. And in particular, the induction axiom is very important because that's what this whole thing hinges on. Now, notice I call these pianos axioms, and although I do a lot of misspellings, this is correct spelling because this is not anything to do with music. This is the name of a mathematician, Piano, so that's a P-E-A-N-O. And Piano's axioms are what are used then to develop the natural numbers and begin that process. Now, even at this point, we have introduced the ideas of associative and commutative and distributive, because you have two operations, plus and multiplication, and they obey these various rules. And in fact, we even have a multiplicative identity. Any natural number times 1 is the natural number. Now, very quickly, we want to add 0 into this, and generally speaking, I just add it as an extended natural number system, and so this would be n with one more element, 0. And I like to do that because I like to talk about 0 independently, because as you know, it is the additive identity. That's basically what distinguishes it from all other natural numbers. It's the additive identity. But then we use a distributive law to prove that a times 0 has to be 0. Now, at this point in time, we derive the basic properties of this extended natural number system, as I've sort of indicated very quickly here. And we observe that under multiplication, we have a semigroup, but under addition, we don't even have a semigroup. Well, we actually have a semigroup under addition as well. And so now the question is, what about inverses? Now, you really got two ways to go on this. You can either do the fractions first, the multiplicative inverses, or you can go to the full set of integers with the additive inverses. I probably, at this point, would prefer to go to, I'll call them the positive rational numbers. And so this would be all numbers of the form P over Q, where P and Q are natural, and Q is not 0. And then we introduce multiplication of this set and addition, and we point out now that we now have a multiplicative inverse. Namely, if you have P over Q, where P is non-zero, then if you take Q over P, you get 1. So this is the inverse. The multiplicative inverse then of P over Q, and we use this notation, is just Q over P. And of course, in this example, then neither Q nor P can be 0. Now, once we've done that, and I'm going through this very quickly, I'm not giving you any details, I'm just telling you what we do in the program, then we observe that we don't have any additive inverses. And that means, for example, that the natural numbers are not closed under subtraction. We've talked about subtraction, but there's no additive inverse. So 3 minus 7 is undefined. Now, this is something we talk a little bit about the history of it. Our ancestors really struggled with this a great deal, but they finally figured out that all they needed to do, and by the way, I might add, all along the way, I am laying these numbers out on a straight line. So now we start with the counting numbers, and they go off to infinity. In fact, we introduce the concept of infinite set. And we talk about prime numbers, and that's also an infinite set. We've now added 0. That's still an infinite set. And then we put in a mirror image, which are the negative numbers. And we now have the integers. And what we've added now is we've added additive inverses. Namely, now we have 3 plus a minus 3 is 0. And so 3 minus 7 can be interpreted as 3 plus a minus 7, and that's a minus 4. And you know all about that. And then we also, of course, every time we extend the number system, we have to verify that all of the rules hold. And I'm talking about commutative and associative and so on and so forth. And now, of course, what we have when we finally get z with these two integers, we have what's called an integral domain. And by the way, with z, we again have given up the fractions. We've just talked about the integers. And then, of course, what we want to do is we want to extend this to Q, the set of all rationals, and now we've added the negative rationals in, and we now have a field. Now, I've gone over this very quickly, and I'm assuming that whoever's watching this video understands mathematics, at least somewhat from an advanced perspective. At this point, we also prove that we define the cardinality of a set as the size of the set. And of course, it's finite. We know all about how to deal with that. But in the case of an infinite set, the cardinality of n is equal to the cardinality of z is equal to the cardinality of q. And in fact, this is no surprise to people because people, before they're introduced to the idea, think that all infinite sets are the same size. Of course, we define two sets as being the same size, having the same cardinality. S1 has a cardinality of S2 if S1 and S2 can be put into one-to-one correspondence. That's how you define when two sets have the same cardinality. And so far, we can easily demonstrate that all these sets do. Now, at this point, we are up to the point where we now have the rational numbers. And this is approximately where the Greeks were, only we've got positive and negative rational numbers. And these are the numbers that we have used in ordinary math. And we put them out on a number line, and every point on the, or every rational number corresponds to a point on the number line. So all rationals, every rational, corresponds to a point on the number line. And they've learned all about this really in the this is not a surprise. They've already know that heuristically from the first 6 tiers, but now we are beginning to do all this in a more rigorous way. Now, at this point in time, we point out the first crisis in mathematics that hit our ancestors, and that is that the polynomial x squared minus 2 equals 0 has no solution. That is rational. So I'll say no rational solution. In other words, what I'm saying is if you solve this equation, you get the square root of 2 as the root, and this is not rational. Now, what we have pointed out back in the first 6 tiers, actually, is that a rational number has a repeating decimal expansion. And we've actually pointed that out then. And any repeating decimal expansion is a rational number. So these are kind of go together. And so what this means, of course, is the square root of 2 does not have a repeating decimal expansion, but that isn't how you prove it's not rational. There's other slicker ways to do it, and it's an easy proof. And the Greeks discovered it. From a Greek's viewpoint, what that meant was if you had a right triangle with sides 1 and sides, two sides were 1 and 1, then this hypotenuse would be the square root of 2. And they thought that it was commensurable with these sides, and that meant the ratio was rational, and they showed that this was not rational or commensurable. And this was a great crisis for the Greeks. They just couldn't accept the idea that there was not a number that corresponded to the length of this hypotenuse. Now remember, we're in an idealized world here. This is an idealized triangle with lengths 1 and 1, and so we're talking about an idealized length. So somewhere up here, and this is approximately 1.414. So somewhere up here, there's a hole in the line. And the Greeks discovered that. And then it turns out it's very easy to show that the square root of any prime is not rational. And in fact, they call them irrational. We got interesting terminologies from our ancestors. Instead of just saying, well, it's not rational, let's call it irrational. And of course, that's kind of a pejorative term, irrational. What does it mean to be irrational? Well, of course, if you're a human being, being irrational means you're not being logical. It's you're being crazy. Well, anyway, we've got lots and lots of holes, it turns out, in the number line. And in fact, you can show that there are many numbers like this. These are called algebraic numbers because of the root of an algebraic equation, and that are irrational, that are real and irrational. Now, you might also, you're quite aware that there are other numbers like the roots of x squared plus 1 equals 0, where this would be the square root of minus 1, that are not only not rational, but they're not even real. In other words, there's no way this can appear anywhere. This is not a hole in the number line. And so this was even worse conundrum for our ancestors, and in fact they call it imaginary, as we've learned in the first tier sixes as far as terminology goes. That was an even bigger problem. So at this point, our ancestors were faced with a dilemma. What do? You've got a number system that you use in everyday math that's quite adequate. Any measurement you ever take will be rational. Any calculation you ever make in the real world is going to be rational. But yet, in the ideal world of geometry, for example, you have these irrational numbers. And indeed, in the world of algebra, you have these irrational numbers. So what's to be done about it? Now, the facts are there's a couple ways that you could go, and that's fine and dandy, but there's one way that's better than others. One way you could go is you could start just adding the irrationals to Q and building bigger and bigger field. Build bigger and bigger fields. So you could start with Q and you could make a bigger field that included the square root of 2. And then you could build a bigger field that was the square root of 2 and the square root of 3. And you could just keep going like this. And then you maybe want to add in, at some point you want to add in I. So you can get an ascending sequence of fields, and this is an infinite sequence of fields. And presumably, if you had the machinery to do it, you could somehow extend this until you came all the way up to some field. I'll call it QAC, which would be the algebraic closure. And all the roots of all the polynomials with rational coefficients can be in this field up here. As a matter of fact, it is possible to do this. Modern mathematicians have figured out a way to do this, and they've figured out a way to create the algebraically closed field of Q. But this is a very, at least in my opinion, this is a very difficult construction. And it's certainly not something that you want to spring onto beginners. Algebraic number theorists do this, but this is not something to do in the beginning. And there's a better, in my opinion, a better and a different approach, and indeed it's the one our ancestors took. You've got this number line, and you got all these holes, and you want to fill in the holes. Now, one way to identify a hole is to find a sequence of numbers that approaches the hole. And this is called a Cauchy sequence. Now, I'm not going to give you details on it. This is just how it's done in general. And what you do is you create a bigger field that now fills in all the holes, and you use Cauchy sequences to do it, and it's called the real number field. And this basically is filling in the holes. Now, this is essentially not algebraic. This is an analytic process. As a matter of fact, what you're really doing, and again, if you don't know mathematics very well, then this is not going to make much sense to you. But what you do is on the rational numbers, you define a distance function, which is called a metric. That's very easy to do. You got number 1, and you got number 2. The distance is just the distance between them. Now, that's harder than you might think if you got holes involved, but nevertheless, that's what you do. You have to use limits. This is sometimes called a metric. And then what you do is you are constructing the completion, they call it, of the metric space. And so what happens in essence is the rational numbers go up to the metric completion. I'll just call it metric completion, and that's called the real numbers. And all the holes are filled in. Now, this is quite a process to do. This is going to take, this is a pretty involved, lengthy argument. You got to use the concept of equivalence relations. And it's one thing to define this field. It's another then to extend the operations. But what you want to have in effect, you're going to have a real field with plus and times on it. The rationals are going to be a subfield with the same operations that are embedded in it, and the rationals are going to be what is called dense in the real field. This is all really essentially an analytical process. Now, mind you, what I've discussed so far is probably 8 or 10 lectures. You got to do this in steps, and you got to explain each step and each new concept. They're learning new concepts as you go. They're learning the idea of a metric space, of a completion of a metric space, and the idea of an equivalence relationship. And all these are things now that the student is learning for the first time, and the student is beginning to develop mathematical maturity. And by that I mean the student is beginning to learn about the machinery, the theoretical machinery, tools, machinery, whatever you want to call it, that modern mathematicians use. They're beginning to learn that. And it's quite a process. There's going to be a big jump in mathematical maturity to get up to the point of understanding this right here, that you've got the rationals are extended to the reals. It's an analytical extension. You've completed a metric space. This is dense in here, and so on. And there's an additional property now the reals have that the rationals did not have. It's called the completeness property, and this is often expressed as the least upper bound property. And I'm not going to tell you what that is. If you don't know what it is, there's not time to teach it to you in this very brief video. Now, something really huge also happens here as a sidelight of this, and that is if you look at the cardinal number of the rational numbers, which, as you know, is the same as the cardinal numbers of the natural numbers. This is called aleph null. I don't know how to make that symbol. Then if you look at the cardinal number of the real numbers, it is bigger. All of a sudden, we have an infinite set that is in some very well-defined and very meaningful way larger than the infinite set Q. And the cardinal number attached to this is called C. And there's a very easy way to prove this, actually, relatively easily. This is actually fairly easy to prove. It's just hard to accept it. It's hard to swallow the idea that there can be two different sizes of infinity. When I first ran across this, I was probably in my early 20s, and I had a hard time understanding and swallowing it and so on. But there's a very slick way to demonstrate it with a proof. In fact, what you can prove is that if you have a set X and you take its power set, the cardinal number of the power set is always bigger than the cardinal number of the set. And this is called, a guy that discovered all this is a guy named Cantor. And you use a thing called Cantor's diagonal method to prove this. So, not only now has the student learned a lot of mathematical sophisticated machinery to do this, but he's also now, he or she, is learning that, gee, there's more to math than I thought. Now there's different sizes of infinity. And in fact, there's a sequence of infinities. If you take the power set of the power set, that's a bigger set. And so you've got a sequence of infinite sets. And that's kind of hard to swallow. Now, the That is the approach, however, that I think is the best approach, and it's the one that's mostly taken today when they finally get around to it. So now what do we got? We started with the naturals, we went to the integers, we went to Q, we went to reals, and now what do we do? Well, at this point, I think what we need to do is what's typically done, and that is we need to go to the complexes. I've indicated in the first, in tier 4, how that's done, and indeed that is what's done. You simply extend this by taking R and attaching one more unit to it, and this is called a degree 2 algebraic extension. I is, so you go up here, and in fact, one way you can do this, you won't understand this if you don't know the terminology, but C can be thought of as the set of all real polynomials divided by the ideal x squared plus 1 generated by that polynomial, and this is how it could be defined. Now, that's not how we define it, but that's one way you could do it if you were an algebraist. And then it turns out that I told you earlier, there's an algebraically closed field at Q. I'll call it QAC, and it's somewhere as a subset now of this complex numbers. Here's an interesting thing. The cardinality of Q is the same as the cardinality of the algebraically closed set. So clearly, there's a lot of numbers in the reals that are not algebraic numbers. So now we learn, this is how man learned it, by the way, there are many, in fact, uncountably many, this is all kind of humorous, many reals that are not algebraic, and that means they're not the root of a polynomial with rational coefficients. And we call these transcendental numbers. So there's two kinds of irrational numbers. There's two kinds of irrationals. There's transcendental and there's algebraic. And these are countable. So these are uncountable. So there's more of them in some sense. So if you look at the real number line, I love this, and you take any interval really, in that interval you'll have a countable number of rationals, and it's dense, as close together as you want to get them, but you've also got an uncountable number of transcendental numbers. So in a sense, there's more transcendental numbers, so it's even denser, if that makes any sense. Now, topologically speaking, forgive me using the word topological, but analytically speaking, they're no more dense. Dense is dense, but there's more of them. And yet, ironically, can you give an example? And it's not easy. The numbers that you're familiar with, none of them are transcendental. At least that was the case when we started. We can create some transcendental numbers with decimal expansions that are very peculiar and show that they can't be the roots of reals, and that's how we first did it. Unusual decimal expansions. And I won't get into that at all. But then we found out, oddly enough, that one of our favorite numbers is transcendental. Pi is transcendental. And that wasn't proven, by the way, until the very late 1800s. And I'm assuming it was proven because everybody says it was, and it's accepted as proven. I've never read the proof. If you lock me up in a room with pencil and paper and ask me to prove that, I doubt if I could do it in any reasonable length of time. Probably never. E is also transcendental. That's the other big number that we're familiar with. That was also proven, a separate proof. So those two numbers are transcendental. And in a way, there's this, I don't know how to put it. I guess in a way that makes you feel good because both of these are arrived at in very analytical ways, not algebraic ways. And when you create a number using an analytical process, there's a pretty good chance it's not going to be algebraic. It could be, but good chance it's not. So at this point now, we have introduced the student all the way up to, and by the way now, C is algebraically closed. I don't think I said that earlier, but if you take any polynomial with complex coefficients, it has all of its roots in C. It's factored into linear factors. That's one of the things that makes C so very, very important. R is not algebraically closed. And that means if you got a polynomial with real coefficients, you can factor it down into linears and quadratics, but some of the quadratics won't factor any further. For example, if x squared plus 1 is one of the quadratic components of a polynomial, then you're done. You can't go any further down in the real. But up here you can. That becomes x plus I, x minus I. So C is algebraically closed. And that's, by the way, why I told you that the algebraic closure of Q had to be contained in C, because C is algebraically closed. So clearly this is in that. And of course, that's all something I point out. Now, I do not, in Tier 7, I do not do the construction of the algebraic closure of Q. That's much too difficult at this level. It's premature, and I don't approve. What I do is I go from N to Z. That's fairly easy to do. I go from Z to Q. That's a little harder, but not very difficult. I go Q to R. That's tough. That's a tough construction. This is the hardest part of all right here. This construction here is the hardest of all. And then once we get to R, this is an easy construction because it's just a degree 2 extension. So we do easy, a little harder, really hard, easy. And those are the constructions. Now, I'm not done. We've gone from, what did I say? You tell me. Naturals to integers to rationals to reals, went up to C, but now I go over and I do hyperreals. And these are the numbers that our ancestors struggle with for a long, long time because they include the infinitesimals. An infinitesimal number is any number greater than 0 that's less than all ordinary real numbers. So if you got the real number line, now we've got the hyperreal number line, you got 1, 2, 3. On the real number line, the only thing on here is real numbers. But if you go to the hyperreal number line, for every, there's numbers on here around 0, I'll call them delta, that are less than any ordinary real number, a positive real number, and they're not 0 either. So they're called infinitesimal because you can't see them. If this is a scale of 0 to 1, then an infinitesimal is truly so close to 0 that you can't see it with any microscope of any magnification. Because no matter what your magnification microscope is, you can find a real number close enough to 0 that's below that magnification. So infinitesimals are truly invisible in a physical sense. In fact, but this is all theoretical, mind you. This is not the real world. I mean, in fact, real numbers don't exist in the real world. Real numbers are a construction, a conceptual construction. The only numbers that you can argue exist in the real world are the integers, really. And the rational numbers they're close to being physically realizable, but even then you can argue that they're not completely realizable physically. But certainly you can't argue that all real numbers are. The square root of 2, for example, has no meaningful physical manifestation. You might say, oh, well, what about the triangle where this is a hypotenuse 1 and 1? Well, this is an idealized triangle. I mean, what I've drawn here, these are thick lines. They got substance to them. And this is an approximate 90-degree angle. This is all approximated. This is all very, very rational. This would have to be for the ideal triangle, which does not exist in reality. There is no such thing as an ideal triangle in reality. At least as far as I know, there's not. And by the way, there's a whole school of mathematicians that hates this whole approach because they just can't accept that there's any meaningful existence to these things. But then there's another school, which is most mathematicians today, that say, oh yeah, these are real. I mean, they exist, even though they're conceptual. They're in our mind. Now we're getting into philosophy, and I'm not going to get into that. It's way beyond my pay grade, as they say, to say what's right and what's wrong here. I'm just telling you the way it is in modern mathematics. And if you're going to become a mathematician, these are things you need to learn about. Now, mathematicians couldn't figure out how to get these infinitesimals or create this hyperreal field for a long time. They created the real field back in the mid-1800s. I'm talking rigorously now, not intuitively. They created these number systems here, and even this intuitively, centuries and centuries ago. I mean, Isaac Newton used it, and they created this one. This was all done intuitively. Now, they struggle with it. As you know, the very fact they use words like irrational and imaginary lets you know how much they struggle with it. But it was all done intuitively and heuristically a long time ago, although it took centuries and centuries to really do it. They didn't do it rigorously until the 1800s. And then they finally started doing it rigorously, which is what I'm presenting essentially in this Tier 7. Because if you're going to be a mathematician, you're going to have to learn rigor. You're going to have to learn the axiomatic method and how to prove theorems in a very good, and this is the time now to begin to teach that. Mind you, this is still high school math. And we're only talking about students that are going to be future mathematicians. I don't think a future physicist or engineer or economist or anybody's going to use math needs to know this rigor. If they want to know it, fine. It doesn't hurt them, maybe. it might discourage them because this stuff is pretty tough, and you got to have a certain mind to do this. In fact, there's a school of thought that all mathematicians are crazy. I'm not of that school of thought, although I've known a lot of mathematicians that I thought were pretty close to being crazy. And since I don't consider myself a mathematician, I guess I can exempt myself. But in any event, this was all done non-rigorously until the 1800s. And then when they did it rigorously, they couldn't figure out what to do with these infinitesimals. Now, they'd been around a long time. They were also treated non-rigorously by our ancestors. Hell, Archimedes used them. Newton used them. Euler used them. But we couldn't get them into the rigorous system, so we banned them in the 1800s. Well, then, in the 1960s, they figured out how to put them back in rigorously. And so now they're back in the fold, and they're done rigorously, and they're wonderful from an intuitive or heuristic viewpoint. I mean, calculus is an awful lot easier to explain and to do things when you've got infinitesimals. I might also tell you that there is a practical version of infinitesimals if you do things right with modern computers, with a modern computer, or even with a modern calculator. I mean, I can use infinitesimals with this $10 calculator to prove things using infinitesimals. I can do it with this $10 calculator. And indeed, I do it in Tier 5. When we teach differentiation, we actually use this calculator to derive derivatives using the infinitesimal approach. It's very easy to do, actually. But it's not rigorous, but it works. and that's why physicists have always used it, and engineers. They never gave them up. Only theoretical mathematicians gave them up. But with modern computers, you can always do it. And in fact, Mathematica does it, of course, as does Wolfram Alpha. So you can use it practically. But now they're also theoretically back in the math fold, even though a lot of mathematicians today still tend to ignore them. Because quite frankly, when you look at most of your calculus books today, they don't use them. They're old-fashioned. The calculus books today still act like we're still back here. They still act like we're pre-1960. Most calculus books, when it comes to rigor, they stop right here. They don't go up into here. And that's a shame because in the 1960s, and after all, that's 50 years ago. We should definitely be incorporating them into our calculus books today more than we are. And of course, I do that in Tier 6, or Tier 5 rather, as you know or may know. Well, this is what I want you to do when we do get into Tier 7. This is how we're going to now begin to bring our math students along, the guys that might want to be professional mathematicians. If they cannot get through these constructions in Tier 7, if they can't buy into this, if they can't understand it, then quite frankly, they're not going to become mathematicians. This is really the foundation of modern theoretical math. It's not advanced theoretical math. This is foundational stuff. Most of this was done in the 1800s. A little bit of it was done in the 1960s, but this is all very foundational theoretical work. And so that's what's in Tier 7. In Tiers 8, 9, and 10, then I go way beyond this and bring people further up into modern math, getting them ready for a career as a mathematician, and that'll have to be discussed on other videos. So I hope you've enjoyed this. It's Dr. Dell, and I will see you on another video. Bye-bye.